The SNAP-8 electrical generating system for spacecraft is being developed at the Atomics International Test Facility for the Atomic Energy Commission and the National Aeronautics and Space Administration. This film depicts the status of SNAP-8 component evolution and systems development through the start of reactor power testing during the summer of 1963. The nuclear system is based on the proven SNAP-2 concept. The nuclear reactor is uranium zirconium hydride, fueled and moderated, and NAC-cooled. The SNAP-8 reactor is designed to deliver up to 600 kilowatts of usable thermal power. The entire SNAP-8 electrical generating system is comprised of the nuclear system and the power conversion system. The nuclear system consists of the reactor core structure, controls, safety devices, and shield. The reactor heat is transferred to a mercury boiler through a closed-loop NAC coolant system. The resulting mercury vapor drives a turbo alternator, which generates 35 kilowatts of net electric power. The mercury vapor is condensed in a heat exchanger, and the liquid mercury is returned then to the boiler. The condenser is cooled by an independent NAC heat transfer loop, which dissipates the waste heat to space. A fourth organic lubricant cooling loop is employed to furnish cooled lubricant to bearings and coolant to heat-sensitive components in the system. All nuclear system operational controls will be contained in the electrical generating system package. Except for the telemetered startup signal, the system is designed to be independent of spacecraft systems. The power conversion system is being developed by the Aerojet General Corporation under contract to NASA. This film concerns the nuclear reactor system being developed by Atomics International under contract to the AEC. The reactor is designed for a NAC coolant outlet temperature of 1300 degrees Fahrenheit with a controlled dead band of approximately plus or minus 20 degrees Fahrenheit and a coolant inlet temperature of 1100 degrees Fahrenheit. During rated power operation, the NAC coolant flow rate is approximately 13 pounds per second with a pressure drop of less than 10 psi through the nuclear system. The reactor is designed for continuous unattended operating life of 10,000 hours in the space environment. SNAP-8 will start in orbit on ground command. Although restart is not required for the flight reactor, the nuclear system is designed to withstand 50 automatic startups during the ground testing program. The nuclear system is comprised of 4 main assemblies: the core assembly, the reflector assembly, the electronic controller, and the shield assembly. The core assembly consists of a 211-rod fuel element array supported between grid plates within a stainless steel vessel. The fuel elements are slightly over ½ an inch in diameter and have an active length of 16½ inches. The core vessel is approximately 9½ inches in diameter and about 2 feet long. The vessel has NAC coolant inlet and outlet connections and contains internal flow control baffles. The reflector assembly is supported on brackets affixed to the base of the core vessel. The brackets support 6 fixed beryllium strips and 6 rotatable beryllium control drums. These are alternately arranged around the core vessel's circumference, forming, when the drums are in, a continuous 3-inch thick external reflector. The control drums are actuated by electromechanical drive systems. By rotating the drums, the neutron leakage from the core is modulated, thus controlling the power output of the reactor. The weight of the reactor, including its separate automatic electric controls, is approximately 550 pounds. At the end of the mission, or in the event of a major system component malfunction, the reflector system will be jettisoned automatically, thereby permanently scramming the reactor. A shadow shield assembly is inserted between the reactor and the power conversion system. The lithium hydride shield is designed to reduce the radiation emanating from the reactor to levels governed by spacecraft and payload material, configuration, and mission. The nuclear system is designed to withstand the conditions anticipated during ground handling, storage, launch, startup, and operation in space, and will be tested under simulated conditions. This core is being prepared for vibration testing. A probability of successfully completing a 10,000-hour mission life of 93% is a design goal. This goal includes the non-puncture probability from micrometeoroids. The SNAP-8 fuel is a blend of uranium metal and zirconium sponge. The blend is compacted and then sequenced through a multiple melting and forming process to assure uranium homogeneity. The final extruded product is a rod of SNAP-8 fuel element dimensions. The rods are hydrided by a carefully programmed pressure temperature time cycle. The resulting hydrogen content of the material when at 1,300 degrees Fahrenheit is approximately that of ordinary water at room temperature. The hydrided rods are clad with chromized Hastelloy N tubes. To minimize hydrogen loss from the fuel at reactor operating temperatures, the internal surface of the cladding tube is coated with a thin ceramic coating. A similarly coated end closure cap is placed in the end of the tube. This ceramic coating reduces loss of hydrogen by diffusion through the cladding tube by several orders of magnitude. Quality control checks are sequenced throughout fuel element manufacturing to conserve material and assure reliability of the final product. These specially designed furnaces are used for checking hydrogen losses at reactor operating temperatures. Although the hydrogen barrier coating used on currently produced fuel elements is performing well in the development tests, improved coatings are presently being developed for the flight systems. Control and handling of all fissionable materials during fuel element fabrication is done in accordance with safety procedures established by the Atomic Energy Commission. After final testing and inspecting, the completed fuel elements are packaged for shipment to the reactor assembly area. Since the SNAP-8 components are based on their SNAP-2 counterparts, a considerable amount of technology is available. The components on SNAP-8, however, operate at significantly higher temperatures than on SNAP-2. Most of the moving parts on the SNAP-8 reactor operate in the temperature range of 600 to 1,100 degrees Fahrenheit. Not only must reactor components be designed for full lifetime operation in space, but they must be capable of performing at ground test conditions. Oxidation of beryllium components, such as the reflectors shown here under test, is a problem during ground testing where moisture and oxygen are present. Catastrophic failure has been observed within hours when unprotected beryllium has been tested at SNAP-8 operating temperatures in laboratory air. Protective coatings are under development. To date, an anodized coating appears to hold promise as an interim solution. The ultimate answer to this oxidation problem is to eliminate it by conducting ground tests in ultra-high vacuum environments. Using specially designed friction test equipment as seen here, materials are being investigated for control drum actuator and drive bearings. Graphite bearings are being developed which seem satisfactory for space applications. Graphite bearings, however, also require a vacuum environment to prevent oxidation during ground tests. Tests for determining self-welding behavior of materials are shown being performed here in a high vacuum environment. This self-welding problem involves separation of the core, reflector, and shield at the end of reactor operational life. Mating surfaces will be held together for 10,000 hours with no relative motion. Electromechanical control drum drive systems must operate at temperatures around 1,000 degrees Fahrenheit and will see radiation doses estimated to be 10 to the 19th NVT of fast neutrons and 10 to the 11th rads of gamma radiation. Control drum locations must have maximum position reproducibility and minimum accumulated error through the entire operating range to meet these requirements. Alternate actuator and drive concepts are being developed in parallel efforts. A continuing basic research program is being conducted. This program is planned to complement the development and design of flight system components by determining the effects of the SNAP-8 environment on individual electronic and mechanical elements. Special facilities are being employed for the development of SNAP-8 shield fabrication techniques. The SNAP-8 shield utilizes lithium hydride to attenuate the neutron dose to the payload. Lithium-7 is used instead of natural lithium. The heat generated in the shield is thereby reduced by a factor of 10 and thus prevents melting of the hydride. The lithium hydride is fabricated using a casting process. The resulting product has a high thermal conductivity and a lower operating temperature than can be expected in similar shields produced by hot pressing. The major effort in shield development is the development of the casting procedure. Fabrication techniques for the shield vessel with its internal structural partitioning and lithium hydride crack controlling reinforcement are also being developed. Flight system shield designs will be tailored for individual missions. A process development shield is shown here being removed from the casting furnace. This should attenuate SNAP-8 reactor radiation to a total neutron dose of 10 to the 13th NVT fast neutrons and the total gamma radiation dose to 10 to the 7th rad at a payload 8 feet in diameter located 15 feet from the reactor. This shield weight is 1,100 pounds. To develop a fully qualified and reliable SNAP-8 nuclear system that meets all power and endurance criteria, a step-by-step development program is being followed. The developmental reactor mock-up test is an environmental test of the prototype nuclear system composed of flight-type hardware representing the present state-of-the-art, but which uses mock-up fuel elements. The mock-up is shown here in early stages of assembly. Tests on this system are planned to prove that the SNAP-8 mechanical and electrical systems are indeed feasible for the environments anticipated. The design of the second generation nuclear test system will be based on design and fabrication experience, bench testing, and initial thermal testing of the developmental reactor mock-up. The developmental reactor test in the SNAP-8 program will be performed in the ground prototype test facility shown here, now nearing completion at the AI Field Test Laboratories at Santa Susana. The ground prototype system will incorporate the prototype reactor coupled to the prototype power conversion system. The system will be arranged in a non-flight or breadboard configuration to facilitate access during the test. The primary objectives of this test are to develop and demonstrate automatic startup and control of the complete electrical generating system and to demonstrate 10,000 hours endurance. An environmental laboratory is in the early stages of design for the eventual 10,000-hour proof testing of the flight prototype electric generating system. The flight prototype system will be the final nuclear test and the second complete system test in the SNAP-8 program. This system will be operated in a flight configuration. Grading and excavation for the test vault has been started. Parallel to the nuclear tests on the flight prototype system, an identical reactor with mock-up fuel elements will undergo extensive mechanical proof testing. Live reactors of this same design will be delivered to NASA upon successful completion of proof tests and will be ready for use upon completion of 90 days of operation of the flight prototype system. On September 17, 1962, the first critical experiment in the SNAP-8 program was conducted at Santa Susana. This preliminary experiment was performed with the S8ER core at low power. The S8ER test program is essentially a concept proof test. Its specific objectives are to demonstrate reactor operation and determine reactor performance characteristics at rated power and temperature. The test will provide experimental data upon which to base the design of the flight reactor, particularly with regard to reactor stability, temperature coefficients, and hydrogen loss rate. Although the S8ER is reflector controlled, it does not use flight design control drives, actuators, or safety devices, nor does it include a flight shield. The test building was designed for and was previously used to perform the initial power test on the SER, the SNAP-2 experimental reactor. That test established the feasibility of the general SNAP reactor design concept employing uranium zirconium hydride fuel. Using handling equipment available from the sodium reactor experiment and a carefully planned shielded sequence of operation, the SER was removed in June 1961. The building and service systems were modified by November 1961. Then the S8ER heat transfer system and control room instrumentation were installed. The reactor operates in a 3-foot diameter steel containment vessel enclosing a helium atmosphere, a measure calculated to retard oxidation of the beryllium reflector. A 4-foot thick concrete shutdown shield is placed between the reactor and the control drum actuators so that actuators and position indicators may be serviced. The reactor heat is transferred from a shielded and contained NAC primary loop through an intermediate heat exchanger to a secondary non-radioactive NAC system, which in turn dissipates the reactor heat to the atmosphere. A removable clean room is placed over the containment vessel prior to reactor core installation. The core was fully assembled in a critical facility adjacent to the S8ER test building. Neutron-absorbing rods were inserted, and the entire unitized core was safely transported to and loaded into the containment vessel. The first of the program series of the SNAP-8 nuclear power tests started in mid-1963.